Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it.
This is the beginning of chapter 3. Now, chapter 3 is differentiation. Chapter 3 contains the bulk of what this course is about. All right. Um, Calculus 1 is also sometimes referred to as differential calculus. So this is really the chapter that the grand majority of this course is really based on. All right. So 3.1. 3.1 is called the derivative, and the tangent line problem. All right, so here we go. First, let's remember what a tangent line is. All right, and from geometry, if you recall, if you had like a shape, right? Let's say a circle, and I want the tangent line somewhere. Well, this is essentially what a tangent line is, right? It's a line that touches the shape at one point, but just at that one point, right? Um, in terms of calculus, what we can say now is, let's say that we have some function, right? Some curve. And in here, well, we can come up with places where we might be necessarily interested in the tangent line, all right? And in here, I'm drawing three different tangent lines at three different points, all right? Now, in each one of these 3 points, I mean, those are the tangent lines, right? But the question really arises of how do we find that line, that specific line, all right? But notice here that, well, for each, in this case, in this first line right here, in this scenario, we already have a point. So to find the equation of this line, well, there's only one thing that we still need, and that would be the slope. Because if you recall, there is a point slope formula that we can use to find the equation of a line. So in here, we're already given the point, so we still need the slope. So that's really what this is about. Now, before we talk about that, let's consider so this was a tangent line. But let's consider first something called a secant line. And again, you may or may not recall, but a secant line is one that crosses our shape and hits it at two different points. All right. Now, this right here is essentially how we're going to start to figure out what a slope for a tangent line is. All right. So this is the main idea. Let's say that I have my curve. All right. Let me set this up. Let's say that I have this curve. All right. And perhaps I'll shift down a little bit. Let's move this a little bit down. All right. So here we go. So let's say that I had this curve, right? And actually, let's make it a little curvier, just for the sake of this example. There we go. Way curvier, better. So now, if I start by taking this point and this other point, right? Let's say that this point is at x1 comma y sub 1, and this point over here is at x2 comma y sub 2, right? And what I want you to notice here is that, well, in here, this distance is delta x, right? In other words, x sub 2 minus x sub 1. And then this distance over here is delta y, which is y sub 2 minus y sub 1. All right. Now, if I draw a line, a secant line, going through these 2 points, like so, all right, if I draw that line, well, in here, let's The slope for this line, let's consider that. The slope for this line would be y sub 2 minus y sub 1 over x sub 2 minus x sub 1, right? But we don't really care about this line because this is the secant line. So what can we do here? Well, let's consider the following. And let me just copy and paste it. There we go. So now over here, let's say that instead of x sub 2 being all the way over there, so I'm going to move this, we put it a bit closer, right? So let's say that it was around here at this x sub 2. And now this is delta x. But now our y changes, our y sub 2 changes. It's no longer all the way up here. It is just right here, y sub 2. Now, in here, I want to consider this secant line, right? And I mean, the slope is still the same idea, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. But notice that now, by making this distance between the x's smaller, this secant line, it's starting to look like a tangent line, all right? And in fact, let's do this one more time. So I'm going to copy from this one now. And now, let's say that instead of x sub 2 being all the way out here, it is even closer, like right there. There's our x sub 2, right? And a whole bunch of stuff here is going to change. So now, here is the other point, and here would be y sub 2. Now this ends up being our y sub 2 minus y sub 1, and this ends up being our x sub 2 minus x sub 1. And now we've got this line. All right. Perhaps I'll make it look slightly more like a secant line. There we go. That's a little bit better. All right. So again, the point here is, well, these distances, this distance is getting smaller and smaller, right? And while that distance is getting smaller and smaller, we're getting something that's closer and closer to a tangent line, right? We started with the secant line, and that secant line, well, by making this distance smaller, it starts to look like a tangent line, and now there, it's even look closer. It looks even closer to a tangent line. So in terms of calculus, what's happening here really? Well, what's happening here is that we're really doing a limit, all right? So in here, what we're doing is we're letting this delta x, we're letting that delta x go to 0. So let's see what happens as delta x goes to 0. Well, what do we get? And I'll paste this drawing again, but now I'm going to remove a bunch of things out of this. So what we end up with is something like this. Well, yeah, I guess I can get rid of that. Oh, I didn't want to get rid of that. Just the point. There it is. All right. So in here, as x of 1, as delta x goes to 0, then we end up with this line. And that line, that would be the tangent line. All right. So let's get a definition for finding the slope of a tangent line. All right. So definition of a tangent line with slope m at point C. All right. So here we go. So if f is defined on an open interval containing C, And if the limit, this following limit, then I'm going to write here, if the limit, so limit as delta x goes to 0 of, well, I'm going to say delta y over delta x, right? Because that was our definition for the slope of a secant line. So that limit, which we're going to rewrite as, well, as delta x goes to 0, as f of c plus delta x minus f of c over delta x. We're going to define this to be m, so I'm going to say m. So if that limit exists, then the line passing through c comma f of c, too many parentheses, with slope m is the tangent line to the graph of f at the point c comma f of c. All right. So in there, essentially what we have here is a way to find slope, right? The slope of any function. And let's see here, oh, the slope of any function at a specific point. Now let's see why the way that I wrote it would make sense. Let's say that instead of naming this x sub 1, let me actually copy and paste this. I think I already copied it, so let's just paste it. So in here, all right, let's edit this. So let's say that I called this first point, instead of x sub 1 comma y sub 1, let's say that I called it c comma, that point is c comma f of c. All right, and then if this distance right here is delta x, then x of 2 will be called delta x plus c, right? Or I can write it instead as c plus delta x. That makes better sense. C plus delta x. And I'm going to get rid of this part down here. All right, so that's delta x. So this point is c, so that's c plus delta x, making this point up here, well, f of c plus delta x. And now our slope definition over here of y sub 2 minus y sub 1 over x sub 2 minus x sub 1, well, instead of all those things, it's going to be f of c plus delta x minus f of c, right? This one was originally y sub 2. This was originally y sub 1. And on the bottom, x sub 2 minus x sub 1. Recall that this one was originally x sub 1, and this one was originally x sub 2. So x sub 2, which is c plus delta x, minus x sub 1, which is just c. Well, if you notice in the bottom, the c's cancel out, so I just end up with delta x on the top. I have f of c plus delta x minus f of c. And that is the formula that I had inside here. All right, so that's where that comes from. And all we're going to do with that is make sure that this distance, delta x, goes to 0. All right, now, just real quick, in here, the book uses delta x a lot. Instead of delta x, I'm not going to be using delta x. I'm going to be using the letter h. So I'll make a note here. Note, if I, so, not let, if I let delta x be equal to h, or instead, that's not how you define variables. If I let h be equal to delta x, way better. What I get here is that then the limit as delta x goes to 0 of f of c plus delta x minus f of c over delta x, then I could rewrite that as the limit as h goes to 0 of f of c plus h minus f of c, all of this, over h. All right. So again, in general, I'm going to be using the letter h when I write this formula, but it's the same thing as what the book does with the delta x. All right, so let's do an example. Let's do an example here. So example A. Find the slope. Well, find the slope of f of x equals 2x minus 3 when c equals 2. All right. So and here is telling me to find the slope for a function. Well, let's do it with this limit definition of the slope. So we're going to say here, well, since I need to use the limit definition of the slope, well, m is the limit as h goes to 0 of f of c plus h minus f of c all over h. And we're saying c is equal to 2. So what we have here is the limit as h goes to 0 of f of 2 plus h minus f of 2, all of this over h, which gives me, if I plug in 2 plus h into the x, I have 2 times 2 plus h minus 3. That's my f of 2 plus h minus f of 2, which is 2 times 2 minus 3. And all of this over h. And look at that, I forgot to write the limit in the front. Don't do that. Always write the limit unless you've actually evaluated it. And I didn't evaluate it yet, so I must write the limit. All right. So that gives me now the limit as h goes to 0 of, if I distribute the top and get rid of all these parentheses, well, I'll get rid of the parentheses in the second one. So in here, 2 times 2 is 4, 2 plus 2 times h is 2h, and then we have that minus 3, minus 2 times 2 is 4, and then that minus 3, all of this over h. Now, let's see what cancels out here. I have a 4 minus 4. Well, 4 minus 4 is 0. I have a negative 3 minus negative 3. That really means negative 3 plus 3, so those cancel each other out. Now what am I left with on top? So I have the limit as h goes to 0, all right, that's its limit somehow, and I end up with on top 2h, that's it, over h, which gives me, well, these h's cancel out, so I have the limit as h goes to 0 of 2, which is just 2. Done. But I mean, we already knew that, right? We already knew that because I have a linear function. And with a linear function, the slope is there, right? It's mx plus b. So I already had that. But I mean, at least this shows you that it's true for the linear case, right? So let's see what happens if I'm not working with a linear function. All right. So b. Let's say that the question was find the slopes of the tangent lines of f of x is equal to x squared plus 1 at the point 0, 1 and at the point negative 1, 2. All right. So in here, well, we're given 2 points. So what I'm going to do is I'm going to find the slope, which again was the limit as h goes to 0 of f of c plus h minus f of c over h. Right. I'm going to find the generic slope before I consider what these points are. So let's see what happens here. So I have the limit as h goes to 0 of f of c plus h. So that's going to give me c plus h squared plus 1 minus f of c. So that's going to be c squared plus 1. All of this over h. Now let's go ahead and simplify this even more. So we have the limit as h goes to 0 of c plus h quantity squared, that's c squared plus 2ch plus h squared plus 1, distribute this negative, minus c squared minus 1 all over h. At that point, we see a few things cancel out. C squared cancels out with c squared, right? C squared minus c squared. 1 cancels out with a minus 1. And what you'll notice now is that everything in the numerator that wasn't canceled out, it still has an h left, all right? And as it should. If at this point you ended up with something that didn't cancel out that still had an h, then you probably messed up somewhere. But because everything has an h now, I can factor out an h, and I'm left with 2c plus h, all of this over h. At this point, these h's cancel out, and I end up with the limit as h goes to 0 of 2c plus h. And now I can plug in h going to 0, because if h is 0 now, this gives me just 2c, right? Now recall that we were trying to figure out what the slope was at these given points. Each of these points is in the form of c comma f of c, all right? So I have the point now. So in here, this is c, and this is c. So let's look at the first point. The first point being 0, 1. So for the point 0, 1, we get that the slope is, well, we just said it was 2c. In this case, it's 2 times 0, which is 0. All right. So that was at the point 0, 1. At the point negative 1, 2, right? That was the other point, right? Negative 1, 2. So in there, we get that the slope is, again, 2 times c, but in this case, c is negative 1, so 2 times negative 1, which is negative 2, all right? So that's what we have there. Now notice that now that I have the slopes and I've got the original points that they came out of, I can figure out the equation of the tangent line at each of those. We'll do some examples with that later, but for now, I want to make a note here. Note. If the limit as h goes to 0 of f of c plus h minus f of c over h, if that gives us either positive or negative infinity, all right, then the equation of the line the equation of the tangent line, the equation of the tangent line is x equals c, and it is a vertical tangent line, and it is vertical. So by that, one possible way that can look like is, well, let's say that I had that there. Well, this line would be tangent there, right? But it would also be vertical. Now, let's say that you want to see it in the terms of a function. Well, let's say that I had a function that looked like this. All right, and there, around here, we have a vertical tangent line. All right, so it is possible for a function to have a vertical tangent line. Now, that was the derivative at a point, all right, because it was the slope at a point. So now let's talk about the derivative of a function overall, not necessarily at any specific point. So this is the limit definition of a derivative. And this is what it says, all right? This is the definition. And this is how we write it. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x, all of this, over h, all right? That would be the derivative, all right? So let me actually add some words here, but I want to shift this. So the derivative of f at x is this thing. F prime is equal to limit as h goes to 0 of f of x minus f of x over h, provided the limit exists. Right? Recall that there are some cases when the derivative does not exist. Right? Now, I want to make a quick note about how I was pronouncing this. So I'll say note. This symbol is pronounced f prime of x. All right. The process of finding a derivative, the process is called differentiation. Right? And a function is differentiable at x when its derivative exists. All right. So in other words, if this limit didn't exist for some reason, then the function would not be differentiable at that point. I also wanted to point to other notation. All right, because that f prime is not the only kind of notation. So we use discussed f prime of x. By the way, that prime is essentially like an apostrophe. All right, but we pronounce it prime. So f prime of x, we can also have dy dx. That means the same exact thing. We can also have y prime. We can also say things like d dx of f of x. All right, and one notation that you will not really see until you get to Calc 3, if you do take multivariable calculus, would be something like this. All right, but again, this notation, so it still says the derivative of y with respect to x. All right, but that notation does not really come in until you do multivariable stuff. But in here, all of these notations mean the same thing. F prime dy dx, y prime, the derivative of f of x with respect to x. All right, all of these mean the same thing. So let's go ahead and practice finding some derivatives then. All right, so here we go. Example C. Find the derivative of f of x is equal to x cubed plus 2x. All right, so here we go. So the derivative, well, anytime we want to use a formula, we need to write it down, right? And here the formula is the limit as h goes to 0. That's our definition, right? F of x plus h minus f of x over h. By the way, this fraction here, you should have been recognized it by now, right? This is the difference quotient, all right? So we're going to take the limit as h goes to 0 of the difference quotient. And in this case, we end up with, well, the limit as h goes to 0 of x plus h cubed plus 2 times x plus h. And so that's our f of x plus h minus f of x. So x cubed plus 2x and all of this over h. So now, at this point, we're going to say, well, let's expand this, all right? In here, this expands to the following. So we have the limit as h goes to 0 of x plus h cubed becomes x cubed plus 3x squared h plus 3xh squared plus h cubed, all right? This right here, I mean, I have personally memorized it by now. That's what x plus h cubed becomes. But if you don't know how to do that just on the top of your head, you can go ahead and start doing it like x plus h times x plus h times x plus h, and begin foiling them out two at a time. All right. So that's that first piece. Distribute that 2, so plus 2x plus 2h. Distribute that negative, negative x cubed minus 2x. All of this over h. So at this point, I get the limit. Actually, before that, let's see what cancels out. Let's see what cancels out. We've got an x cubed here and an x cubed there. That cancels out. We've got a 2x here and a negative 2x there. That cancels out. Notice that everything that's left here has an h. The only stuff that didn't cancel out still has an h. So now I get the limit as h goes to 0 of, now because we just said that everything here had an h, I can factor an h. And if I factor an h, I'm left with 3x squared plus 3xh plus h squared plus 2, all of this over h. At that point, these h's cancel out. Now we have the limit as h goes to 0 of 3x squared plus 3xh plus h squared plus 2, right? And since h is going to 0, well, we have a few things here that go away. This goes to 0, this goes to 0, so I end up with just 3x squared plus 2, all right? And that will be my derivative, all right? So in here, I can say that f prime of x, our derivative, is 3x squared plus 2, all right? And if I wanted to figure out what the slope at any given point was, I could just plug it into here, right? Because overall, the derivative is the slope of the function at a specific point, right? Just like we had defined it up here. But anyway, let's do another example. All right, so D. Find f prime of x for f of x being equal to the square root of x minus 1. Then find the equation of the tangent line at the point 5, 2. All right. So find f prime of x for f of x equals the square root of x minus 1, and then find the equation of the tangent line at that point, 5, 2. So, all right, so first I want to find f prime of x, and we know that f prime of x, by definition, it was the limit as h goes to 0 of f of x plus h minus f of x, all of this over h. All right, always write down the formula whenever you're starting with anything. All right, so there we go. So that's our definition, our limit definition of a derivative. So what does this do? So we have the square root of x plus h minus 1 minus the square root of x minus 1, all of this over h. And look at that, I messed up by not writing limit. Always, always, always write limit, unless you actually evaluate it. So the limit as h goes to 0 of that. All right, well, in here, as written, well, there's not much that I can do, all right? But in general, there's always two things we can do with any math problem, no matter what the problem is, all right? The two things are add 0, adding 0 doesn't change anything, and the other one is multiply by 1. In here, we're going to multiply by 1, but that 1 is going to be the conjugate of what we have here. So plus, you know what, perhaps I'll copy that to the next line to make it fit better. This way I don't get, all right, so in here, we're going to say that this is equal to now, to this. All right, so now I said we're going to multiply by 1. That 1 is going to be the conjugate of that numerator. And the conjugate of the numerator is the square root of x plus h minus 1, right? These parentheses aren't doing anything, but in there, but I guess I can rewrite them. And then plus the square root of x minus 1. All of this over the square root of x plus h minus 1 plus the square root of x minus 1. All right, so I multiply by the conjugate. Recall that when I take the product of conjugates, a plus b times a minus b, I end up with a squared minus b squared. All right, so that's what we're going to do here. So what I get now is this becomes the limit as h goes to 0 of a squared minus b squared. So it's going to be the square root of x plus h minus 1 squared minus the square root of x minus 1 squared. All of this over, don't distribute the bottom, leave it as h times the square root of x plus h minus 1 plus the square root of x minus 1. And I guess I could put parentheses there. It doesn't change anything. All right. Now in here, well, let's simplify this down a little bit. So we have the limit as h goes to 0 of, and the numerator square root squared just becomes x plus h minus 1 minus square root squared. That becomes just x minus 1. On the bottom, well, on the bottom, all we need to do is rewrite it. And instead of rewriting, I'm just copying and pasting. All right, cool. So now, at that point in the numerator, let's see what we can do. We have a few things that cancel each other out. In here, this x, so I have this x minus this x, well, those are going to cancel out. I have this -1 minus -1, that's really -1 plus 1, so those cancel each other out. So what am I left with on top? On top, so we have the limit as h goes to 0 of, the top is just h, right? That's the only thing that was left. On the bottom, I have h, so we have times the square root of x plus h minus 1 plus the square root of x minus 1. Now, we see that these h's cancel each other out, right? There's an h on top and an h on bottom. Perhaps I'll do them with different color. All right, cool, way better. So now that I did that with a different color, we can continue. So those h's cancel each other out, so we have the limit as h goes to 0 of 1 over the square root of x plus h minus 1 plus the square root of x minus 1. But we were taking the limit as h goes to 0, right? So if h goes to 0, I'm left with 1 over the square root of x minus 1 plus the square root of x minus 1, right? And, well, apple plus apple is 2 apples. Well, so I have 1 over 2 apples, but that apple was radical x minus 1. And there you go. So in here, what we found was that f prime of x is equal to 1 over 2 radical x minus 1. But that's not all that we wanted here. We also wanted, so that was the first part, find f prime, right? That's what we did. But now we need to find the equation of the tangent line at 5, 2. All right, so let's see what happens. So first, let's figure out what the slope is. So we're going to figure out the slope at the 0.52. So that's going to give us the slope, which is f prime of x, but in this case, we're going to be plugging in the x value. So f prime of 5, which is 1 over 2 times the square root of 5 minus 1. Now 5 minus 1 is 4. The square root of 4 is 2. 2 times 2 is 4. So I end up with 1/4 there. All right. Perhaps I'll do it in 2 steps. So this was 2 times the square root of 4, right? 5 minus 1 is 4. The square root of 4 is 2, so this is just overall 4. All right. So now, that is my slope. And we've got a point. Slope, point, point, slope. We have a formula for that. All right. And the formula that I'm implying here is y minus y sub 1 is equal to m times x minus x sub 1. That's our point slope formula. All right. Our point slope formula, because we have a point and we have a slope. So now in this formula, if I rewrite it, so I have y minus y sub 1, that is our y value here, that 2. So we have y minus 2 is equal to m. M was 1/4. So 1/4 times x minus 5. All right. So at this point, well, let's distribute that 1/4. So I have 1/4 x minus 5/4. I'm also going to add this 2 to the other side. So I have plus 2. So that's what I get for y equals. But notice here that 2 is equal to 8/4. Right? And the reason I want that is because I want to combine it with these negative 5/4. So I have 1/4 x, well, negative 5/4 plus 2, negative 5/4 plus 8/4 is positive 3/4. And that is the equation of our line. All right, y equals 1/4 x plus 3/4. Now, graphically speaking, what did we find? So I'll give a generic idea as to what we just found. All right. Let's see. I'll try to do this accurately. And we're going to go through these points. All right. And this is going to be my function. All right, that's essentially what my function is. And every single one of these is just going up by 1. All right. Now, what we found here was that at the point, where is it? 5, 2. Oh, look at this. I messed this up. This is shifted over incorrectly, but that's okay. We can move this a little bit. There we go. All right. Slightly more. Close enough. All right. So there we go. Now it's correct. Now we had the 0.52, right? Here's the 0.52. 52. And at that point, we have this tangent line. That's slightly off. Let's make it better. Ooh, but better, I said. Something like this, right? So that's the equation of our, and I mean, that's our tangent line. So in here, this is y equals 1/4 x plus 3/4. And that function was f of x was equal to the square root of x minus 1. All right. And over here, this point is at 3/4, right? Because that is our y-intercept. All right. So visually, that's what we found. We found the equation of that tangent line. All right. Now, let's do this again, but for a different problem. So semi-stack instructions. Find f prime of x, right? So find f prime. You know what? I want to rephrase the problem. I'm going to say, just so that you see another way to ask the same question. Find the equation of the tangent line of f of x is equal to 3/x at x equals 4, right? So find the equation of the tangent line of f of x equals 3/x at x equals 4. This is essentially asking the same exact thing, all right? It's saying find f prime and then find the equation given that point, all right? So now let's see what happens here. In here, well, first I need to find f prime of x, right? Because what I need here for a tangent line, I need a slope and a point. A slope and a point. So first let's find the slope. So in here, the slope is given by f prime of x, which in this case, again, is the limit as x, that is x, the limit as h goes to 0 of f of x plus h minus f of x, all of this over h. In this case, that means the limit as h goes to 0 of 3 over x plus h minus 3 over x, all of this over h. Alright, I personally don't like writing fractions on top of fractions like that, so I'm gonna rewrite that. In general, we know that if I had something like a over b, that would be the same thing as saying 1 over b times a, right? Those two statements are equivalent. So I'm going to apply that idea here. So what I have here is really the limit as h goes to 0 of 1 over h times 3 over x plus h minus 3 over x, right? That was just using this idea up here. Now, at that point, let's see what we can do. Well, what we really want to do is get rid of this h down here, right? But in here, there's nothing that jumps out right away as to how we can do that. But what we can do is combine these two fractions, all right? And the way that we combine those fractions is we come up with a common denominator, and I'm going to write it as x plus h times x. That's our least common denominator, right? Now over here, to go from x plus h to x plus h times x, I gotta multiply by x. So the numerator becomes 3x minus the other numerator, this 3. Well, to go from x plus h times, to go from x to x plus h times x, I gotta multiply by x plus h. So my numerator is multiplied by x plus h as well. At that point, what we can do is this second part over here, let's distribute. So I have the limit as h goes to 0 of 1 over h times 3x minus 3x minus 3h, right? All I did there was distribute the negative 3. All of that over x plus h times x. At that point, we see that some stuff cancels out. 3x minus 3x goes away. So I'm left with the limit as h goes to 0 of 1 over h times, on the numerator, I'm left with just negative 3h. On the denominator, I have x plus h times x. And there, you see that these h's cancel out. So I get now the limit as h goes to 0 of negative 3 over x plus h times x. But if h is going to 0, this part goes away, right? This part right here goes to 0. So I just have x times x. So I have negative 3 over x squared. All right. And that right there is our derivative, f prime. So we found that f prime of x is equal to negative 3 over x squared. All right. Now, that wasn't the end of the problem. The question was, find the slope of the tangent line at x equals 4. Well, so we found, let's find the equation of the tangent line at x equals 4. All right, so we found the general formula for the slope. But what we need here is to plug in the value of 4 to find our slope. So our slope is going to be f prime of 4, which is negative 3 over 4 squared, which gives us negative 3 over 16. All right, that ends up being our slope. Now that we have the slope, well, what do we still need? To find the equation of a tangent line, we need to find the slope and a point, right? We found the slope, now we need a point. How do we find a point? Well, I've got f of x and I've got the x value. So what I can do here is, well, so I need to evaluate the point at 4. So in here, I add that f of 4, well, f of x was 3 over x, so I have 3 over 4. Let me rewrite that. So I'm going to say, let's just recall first that f of x is equal to 3 over x. So that means that f of 4 is 3 over 4, which here this gives me the point 4 comma 3/4. All right. So now that I've got that, now I've got a point and a slope. All right. So now we can use our point slope formula, which was very cleverly named. So we have our point slope formula, right? And all I need to do here is plug in the respective parts. So y minus y sub 1 is 3/4. Is equal to m. M was negative 3/16 times x minus x of 1. X of 1 was 4. So let's just distribute that negative 3/16. So I get negative 3/16 x. Negative times a negative is a positive. The 4 and the 16 reduce. So I end up with 3/4 there. And if I add this 3/4 to both sides, I have another 3/4 there, plus 3/4. So this tells me now that my equation is going to be negative 3/16 x plus 6/4, which is really 3/2, right? 3/4 plus 3/4 is 6/4, and that reduces to 3/2. Now that's the equation of our line. Now let's see visually what we just found. So visually, what we have here is, well, our function looks like this. It was 3 over x, so it looks like this, right? That's what 3 over x looks like. And we have at the point 4, 2, not 4, 2, 4 3/4, right? That point right there is the point 4 comma 3/4, right? That was the point that we cared about. And we're gonna have our tangent line. So our tangent line is gonna look like this. All right, and that is our equation of, that is the graph of the equation of y equals negative 3/16 x plus 3/2. All right, so that's what we found. And notice that it makes sense. It makes sense that we had a negative slope, right? It makes sense that we had a negative slope because this tangent line is decreasing. All right. All right. So now let's talk about differentiation and continuity. So let's put on more. Differentiation and continuity. And let's rewrite that and symbol. So differentiation and continuity. So first, before we talk about that, let's give an alternate form of derivative. So alternate form of the derivative. Oh, that's not what I meant to do. There we go. And it is as follows. F prime of c is equal to the limit as x approaches c of f of x minus f of c over x minus c. Right? Now in here, what I want you to do is I want you to compare it to, and I'll put it in brackets here, compare to f prime of c equals the limit as x as h, excuse me, the limit as h goes to 0 of f of c plus h minus f of c, all of this over h. All right. Now in here, if I let x equal to x plus h, right? That's not what I meant to say. If I let x equal to c plus h is what I meant to say. If I let x equal to c plus h, well then in here that tells me that h is equal to x minus c, right? And if I have, this also implies that if h is going to 0, that tells us that x minus c is going to 0. But if x minus c is going to 0, but if I add c to both sides, this tells me that x is going to c, right? So in there, that's all that happened there, right? This f of c is still f of c. On the bottom, this x minus c, that's just our h, right? And this c plus h is just our x, And lastly, this x going to c is really equivalent to just that h goes to 0. So that essentially there is how that alternative definition is defined. All right. Now, the next thing I want to say here is recall that the limit as x goes to c of f of x exists. So recall the limit as x goes to c of f of x exists if and only if the limit as x goes to c from the right of the function is the same thing as the limit as x goes to c from the left of the function. And they're both just some limit L. All right, so in here, all I'm saying is recall that the definition for a limit was that it exists if and only if it is the same from both sides. So what we're about to do here is we're about to see how a function may not be differentiable, all right, because the limit may not exist. So let's look at some examples here. So I believe I'm at example F. Let me just verify that. Was that last E? Yes, it was. So example F. So example F. Consider f of x being this function. Right? If you don't recall what that is, it was this function, and that was the greatest integer function, right? And it's also called the floor function. All right, so we're going to consider that near x equals 0. All right, so what we're going to see here is what this function is doing near 0. Specifically, we want to try to figure out what the derivative might be. So first, let me remind you what this function looks like. All right, and it's the floor function, so it looks like this: filled in there, open, filled in, open, filled in, so on and so forth. And it does that in both directions. Ooh, not what I meant. So on and so forth. And each of these happens at, so this is -1, -2, -3, -4. This is -1, -2, -3, -4, so on and so forth. I guess I'll add the fourth one since I went to 4 in every single one. All right. So that's what that function looks like overall. All right, but now let's see if we can find the derivative. All right. And I'm going to find it using one-sided limits first. So, and again, we were doing this near x equals 0. So using the alternative definition of the limit, I'm going to write the limit as x goes to 0 from the left of f of x minus f of c. So hold on, I'm approaching c from the left. I'm writing my generic thing first. All of this over x minus c. And in here, since we're approaching 0, I'm going to say, well, we have the limit as x approaches c 0 from the left of f of x minus f of 0. All of this over x minus, so x minus 0. All right. Now, in here, well, what does that mean? That means that what we have is the limit as x goes to 0 from the left of the floor function. All right, that's the floor function minus f of 0, so the floor function with respect to 0, over x minus 0. So the floor function with respect to 0 here, we see that it is 0. So this is just 0. All right. So let's see what we get. We end up with the limit as x goes to 0 from the left of the floor function of x over x. All right. So in here, let's see what's happening here. All right. We're approaching 0 from the left. 0 from the left. So that means that Where we actually are is around here, right? We're approaching 0 from the left. So for example, think of something like negative 0.1, all right? So something like that, all right? Well, any value in between -1 and 0, not including 0, but including -1, when I plug it into the floor function, I get the output of -1. So what I get here really is just -1 over, and if we're really, really close to 0, but from the left, I'm going to say we have a negative tiny number, right? A negative tiny number. Well, negative over negative is positive, so I have 1 over tiny number, all right? So let's see what's an example of a tiny number. So for example, 1 over 1 million. That is a tiny number, right? And this would end up going to positive 1 million overall. So really, what we can say here is that this limit, all right, and I did that in yellow because that's the idea, but the actual limit here, this is going to go to, well, that was only using this tiny number of 1 over 1 million. But what if I used 1 over 1 billion or 1 over 1 trillion? It goes huge very, very quickly. So this goes to positive infinity. All right. Now, let's look at the limit from the other side. If I have the limit as x goes to 0, goes to, yeah, I guess, oh, I'll use the 0 from the right now. We already wrote the definition. We can go ahead and skip to this part of taking the floor function minus floor function of 0 over x minus 0. All right. But now we are coming from the right, right? The limit as x goes to 0 from the right of this thing, the floor function of x over x. And again, let's see the idea of what's happening here. If we're coming from the right, then, and again, we're approaching 0. If we're coming from the right, that means we're on this side over here. All right, so something like 0.1 or even smaller. But notice that everything in this region, everything between 0 and 1, including 0 but not including 1, all of that is at the height of 0. All of that is at the height of 0. So in here, what that gives me is 0 over a negative tiny number. 0 over a negative tiny number. All right. Well, in general, 0 over any number is just 0. All right. 0 over any number is just 0, with the exception of 0, right? Because this, I said negative, I meant tiny, I meant positive tiny number, right? Because it's on the right side. So positive tiny number. But in here, either way, the idea still stands of 0 over a small number is just 0. 0 divided by any number with the exception of 0, right? We can't divide 0 by 0. By 0 divided by any other number just goes to 0. So what we can say here is that this limit actually goes to 0. But notice what happened. From the left, we went to positive infinity. From the right, we went to 0. So in here, we would say that, so thus, the limit as x goes to 0 of f of x minus f of 0 over x minus 0 does not exist. All right, it does not exist, which tells us then, which implies that f of x is not differentiable. By the way, I abbreviate differentiable this way, diffable. So f of x is not differentiable at x equals 0. All right. And one thing that I want you to note about that, and I'll say note, that f of x is not continuous at x equals 0. All right. So it's neither differentiable nor continuous there. Now let's look at other examples where it might fail to be continuous. This might fail to be differentiable. All right. So example G. Let's say that f of x was equal to the absolute value of x plus 7. All right. And we want to see what's happening at c equals -7. All right. We want to see if it's differentiable there. So in here, we're going to say, well, the limit as x approaches c from the left of f of x minus f of c over x minus c. All right. So in this case, we have the limit as x approaches -7 from the left of the absolute value of x plus 7 minus the absolute value of -7 plus 7. All of this over x minus -7. All right. Now here, what does this become? Well, this gives us the limit as x approaches -7 from the left of, well, -7 plus 7 goes away, so on top I'm left with just x plus 7 over x plus 7. That is the absolute value. All right. So before we consider what's happening here, let's look at what we're working with. And perhaps I'll shift some of this down so that we can figure out what's going on with that limit. All right. So here we go. So I'm going to go ahead and draw this function. All right, so you can see what's going on. And so this is what the function looks like essentially. Right? Where this point right here is -7. Now, if you recall, the absolute value of a function, well, in this case, it was x plus 7. The absolute value can be rewritten as x plus 7 for values to the right of our intercept. So for x being greater than -7, I'll say greater than or equal to, and it would be the negative of x plus 7 for values to the left of -7. So in here, well, since we're on the left of -7, what we get here is we have the limit as x goes to -7 from the left of negative of x plus 7 over x plus 7. In here, well, this becomes just negative, well, the limit as x approaches -7 from the left of -1, which is just -1. All right, and that was from the left. But now from the right, so from the right, it will be the limit as x approaches -7 from the right of, well, I'll simplify it to this point over here, absolute value of x plus 7 over x plus 7, right? Everything else would have been the same exact stuff prior to that. But now, since we're coming from the right, we have the limit as x goes to -7 from the right of, well, from the right, that means we're on the right of -7, which we're going to use this definition up here, x plus 7. So we're going to have x plus 7 over x plus 7, which gives us, well, these cancel out, right? Just like these cancel out. It gives us the limit as x goes to -7 from the right of just 1, which is just 1. So in here, since we found different limits from the left and from the right, well, then we know that so the limit as x approaches -7 of f of x minus f of -7 over x minus -7 does not exist, which tells us that f of x is not differentiable at x equals 7. All right. Now, notice here that at this point, it was continuous at that point. All right. It is continuous. Unlike in the previous example, over here in example F, it wasn't differentiable, but it was also discontinuous at 0, right? And here it was discontinuous. But in this case, it's still not differentiable, but it is continuous. So in here, that kind of starts giving us idea of what might be happening. Let's do one more example. Excuse me. So one more example. So this is example H. Before I actually state, this cool theorem. All right. So f of x is x plus 3 to the 1/3, and we're gonna figure out what's going on around -3. All right. So let's see what happens here. So I'm gonna start with, again, the limit from the left and from the right, but I'll go ahead and draw this function first. So you see, so you start getting an idea of what might happen here. So we're going to be around -3. So let's say that this right here is -3, and this function looks something like this. Yeah, let's make it more, something like that. All right, that's essentially what that function looks like. All right, so let's see what happens with this one. So we have the limit as x approaches -3 from the left of f of x minus f of -3 over x minus -3. So this gives us the limit as x approaches -3 from the left of x plus 3 to the 1/3, right? That's our f of x, minus -3 plus 3 to the 1/3, right? That's me plugging -3 into here. All of this over x plus 3, all right? And at that point, well, let's simplify that a little bit. -3 plus 3 is 0. 0 to the 1/3 is 0. And then we have the limit as x goes to -3 from the left of x plus 3 to the 1/3 over x plus 3. Using rules of algebra, we're going to say that this simplifies to 1 over x plus 3 to the 2/3, right? X plus 3 to the 2/3. But now we're approaching 3 from the left. Excuse me, -3 from the left. So you can think of something like -3.1, right? We're thinking about things like this, -3.1. And the idea here is, well, what is this going to give us? We're going to have something like 1 over -3.1 plus 3 to the 2/3, which would be 1 over -0.1 to the 2/3, which gives us given, well, let's do it this way. This is a small fraction squared. Well, that's going to be positive. Cube root, still positive, but there's going to be a small number, all right? Especially if this becomes even smaller, right? If this was like, instead of 1/10, 1 millionth or 1 billionth. So 1 over a small number, well, the reciprocal of 1 over a small number overall becomes a huge number, right? Because divided by a small number, it becomes huge. Think of it as if you had one pizza pie, and you're gonna split it up by a small number of people, you get huge slices, right? Like if you're gonna split it up into 2 people, well, you get half of a pizza each. Anyway, so enough about pizza for now. We'll talk about pizza again when I'm hungry again. But the idea here is that this actually goes to a huge number. So what we can actually say is that this goes to not 0. 0 is not huge. It goes to infinity. All right. Now let's see what happens on the other side. The limit as x goes to -3 from the right of this same stuff, I'm just going to go ahead and skip to the simplified version. So 1 over x plus 3 to the 2/3. All right. And as you'll note here, well, essentially the same thing happens. We have 1 over, but we're coming from the other side now, right? So here, think about like -2.9. All right. So if I have -2.9 plus 3 to the 2/3, well, that gives me 1 over 0.1 to the 2/3, right? -2.9 plus 3 is 0.1. But again, this gives me the same value of 1 over a small number, right? And 1 divided by a small number, again, is huge. It's a huge number. So this also gives me infinity. So both of these gave me infinity, so that gives me that the limit as x approaches -3 to the right of our function of this stuff, x plus 3. Well, I'm gonna write it as f of x minus f of c. Well, c here was -3 over x minus -3. That goes to infinity, alright? Because from both sides it went to positive infinity, but infinity we normally say it does not exist, right? So because it went to infinity, it doesn't exist. So this tells me now that f of x is not differentiable at c equals -3. All right. Now let's see why that would be. This is continuous, right? But in here, if you consider what the tangent line might be, that tangent line would be a vertical line here, all right? Because, well, another way to think about this derivative that we were finding down here is that it's the slope, right? So I have the slopes from both sides going to positive infinity. Well, that makes us that means that we're working with a vertical tangent line, all right? So in this case, we would also say it's not differentiable. And again, I abbreviate differentiable with diffable. All right. So now let's see what theorem this all brings us to. So here we go, theorem. And this is what the theorem is called, or it says differentiability implies continuity, right? And this is what it says. If f is differentiable, so I'm going to say diffable, at c, then f is continuous at c, all right? I want to make a very important note here. Note. This also means that if f is not continuous at c, then f is not differentiable, right? This does not mean that if f is not differentiable, then f is not continuous, all right? That is not what that's saying at all. So let's look at some scenarios here, right? That the scenarios that we just went over. So in this first one says if f is differentiable, then it's not continuous. That's what our actual thing says, right? But it also meant, right, in here, if I look at this alternative version of saying that is, if f is not continuous, then f is not differentiable. That was this first scenario that we did here, scenario f. All right, in there, it was not continuous, so we found that it was not differentiable. The next statement, where is it? It doesn't mean that if it's not differentiable, then it is not continuous, right? Because if we look at scenario 2 here, scenario 2, it wasn't differentiable, right? Or example G. In here, this function, it was not differentiable, but it is continuous, all right? It is continuous here, but it's not differentiable there, all right? And another way to think about this is just because it's not differentiable, it doesn't mean that it's not continuous, all right? So, I mean, this one was another one where it is continuous, but it's not differentiable, all right? So, in here, and perhaps I'll make this a little bolder, continuity, oh, that's way too bold. Let's lower it down a notch. continuity does not imply differentiability. All right, differentiability. It's the other way around. Differentiability implies continuity. All right. So visually, if um, if f of x has any cusps, visually they're sharp turns at c at x equals c, then f of x is not differentiable. So if it had any cusps, it's not differentiable. Another way that it can be not differentiable is if it has a vertical. So here, instead of saying if it has any cusps, we could also replace that statement as if it has a vertical asymptote. Not a vertical asymptote, a vertical tangent line, sorry. If it has a vertical tangent line at C, or we can also say something like, or if it is discontinuous at x equals C, all right? So those are the three scenarios that we just spoke about. All right, that is the end of 3.1.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.